Okay. So the first question should follow from the law of cosines. So basically, just to give you an idea here, the argument is, and what this question is implying, is the if you have a point charge q that is outside a grounded conducting sphere of radius r, okay, and we are trying to find the potential about the sphere, okay, the claim is that if you just take a point charge q prime, right, and you put it in the right spot, inside the sphere, and forget about the sphere, so using the method of images between q and q prime, you'll be able to recover a potential that is the same exact potential as if you were to figure out the potential of the sphere with the presence of that charge there. And so what that does is it simplifies the problem through the method of images. And we're going to go through some of that calculations with this question. So on figure 313, we forget totally about the sphere, and we replace it with a point charge q prime at a point B, where B is less than R. Okay? So the charge q prime is located inside the sphere. Okay, well, and then this is the separation vector. So if we start, so let's start by figuring out what that potential is. From figure 313, you can clearly see from the law of cosines, the separation vector between q and, say, this is point A, for example, will just be r squared plus a squared law of cosines minus 2ra cosine theta. And there's a square root, of course. Yeah? And with the same exact logic, separation vector r prime between q prime and point A is equal, where we're trying to find the potential, is equal to what's this? So we use this triangle now here, right? The one on the left. On the first one we used the entire one. Now we use the one on the left. So this is just r squared plus b squared minus 2rb cosine theta. You follow? This is from the law of cosines. Now, remember, we on the different configuration that we are considering, okay, we have a point charge q with another point charge q prime, such that the ratio is, for this to work, the ratio is q prime over r has to equal q over a. And of course, one is positive, the other is negative, so there's a minus sign here. Okay, so the ratio between q prime and the radius of the sphere is the same exact thing as between the q and the distance a, where you have the point charge. Okay, and so with that said, let's go ahead and see what this ratio is. So we have q prime over separation vector prime Now, what is q prime? Q prime is, from here you can solve for q prime, minus r over aq. So this becomes minus r over a. It got stuck. Let me recover it. Okay, so we were saying from here we could say that q prime is minus r over aq, and so q prime is that minus r over a, q over, and my separation vector prime, I will put this there, yeah? So this becomes r squared plus b squared minus 2rb cosine theta. Okay, now the other piece of this is the distance that we place it at, right, is such that b is, we said that b is smaller than r squared, but it has to be precisely r squared over a for this to work. Okay, so we place the charge, so this distance b here on the figure 313 is just r squared divided by a. You follow? And so if I make that substitution again, I will get minus rq, and then a we said, so from here you can see, from this a will just be r squared over b, yeah? Minus r q. I'm going to try to eliminate q from this, so we get no, actually leave q. Let's see how. So this is minus r. Yeah, the way, let's do this way, minus q over, now r over a is the same thing as a over r in the denominator, yeah, and I'm going to replace b with r squared over a, so basically eliminate b from the equation, because the equation you're trying to prove has no b in it. So this becomes r squared plus b squared will just be r4 over a squared, yeah, minus 2r times r squared over a, yeah, cosine theta. Okay, so far so good. So continuing on, let me bring this r inside, and if we do that, what do we have here? R squared. Why don't we take a common denominator, which is a squared, and cross this a out? So we could do that. So now we've got so far q prime over this. So I'm trying to replace that, yeah, because remember, this q prime is an invention that I've created, yeah. Yeah, so this becomes minus q over okay, bring the r inside, so this becomes a squared over r squared times all this, r squared plus r4 over a squared minus 2r r squared over a cosine theta. Probably this is the easiest way to do it. And then take, now the reason I squared it is because I took it under the square root, of course, and if I distribute it, then you will get AR over R all squared, right? On the second guy it crosses out and you get what, R squared, because R4 over R squared is R squared. And on the last guy you lose an A and an R squared, so these two guys cancel and you get 2RA cosine, 2RA cosine theta, yeah? And there's a square root over this whole thing. Okay, so this is this guy. Okay, good. So you can see there's no more Q prime or B or any unknowns that we've invented into the problem. So now what is the potential? Well, the potential is V is equal to 1 over 4 pi epsilon, yeah, Q over the separation vector plus Q prime over its separation vector. Isn't that the potential from 2 point charges, the first one and the second point charge? Okay, and so this becomes 1 over 4 pi epsilon. Now what's Q? This is we can factor out Q because you know, they both have Q. Actually, let's leave it. So Q over the first separation vector was R squared plus A squared minus 2RA cosine theta minus the second ratio here is here. So I'll just copy the right hand side of this. So minus Q over, yeah, R squared plus RA over R squared minus 2RA cosine theta. Oh, forgot the square root here and the square root here. No? Okay, and of course if you factor out a Q, you will get finally Q over 4 pi epsilon 1 over R squared plus A squared minus 2RA cosine theta minus 1 over, there's a square root here, R squared plus RA over R squared minus 2RA cosine theta. Okay, so this is what he's asking you to prove. This is V, and notice when if we let's check out what happens on the surface of the sphere. So when R equals R, right? Plug it in. What do you get? V equals Q over 4 pi epsilon. What do you expect to get? 0. Let's find out if this is 0, because this is a conducting sphere, right? This is a conducting sphere, so the V has to be 0 at the surface, yeah. Well, let's find out if that's the case. So 1 over, if you put R, you get R squared plus A squared minus 2RA cosine theta. And what's the right hand side? Well, if these two will cross out, then if that happens, and R squared is just small r squared plus A squared minus 2RA cosine theta. Indeed, they are the same, and the answer is 0. Because these two guys go away. So V goes to 0 when R equals R. Yeah? V goes to 0 when R equals R. Okay, now uh, why don't we might as well figure out the induced, so this was part A, yeah? Now let's find the induced charge density on the surface of a sphere as the function of this angle. Okay, now you remember how to do that? Well, if you remember, the surface charge density, well, we know that from the boundary conditions that dV over dN is equal minus sigma over epsilon, no? Surface charge density, that equation is in the book. It's one of the boundary conditions, right? Now, what do we have? Now, N represents R, yeah? This is all happening in the radial direction. This is all happening in the radial direction. So, so in our case, dVn is dVr, right? And we're trying to figure out the surface charge density on the sphere, so that means when R equals R. So, so then this is equal to minus epsilon dV over dr. You agree? And so what we're going to do is we're going to take the derivative of this guy here. Or, yeah. We're going to take the derivative of this guy here. And then at the end, we check it out on the surface. Okay? So let's start doing that. So, this is minus epsilon. Okay. Partial derivative with respect to R. The first term we have, let's leave Q over 4 pi epsilon out. Yeah? Because it's a constant. So, what's the square root? Bring it up there. It becomes half, minus half. So, we've got minus half. Or you know what, why don't we just use the shortcut? You know that the derivative of square root x is 1 over 2 square root x, yeah? So this becomes, well, whatever, it doesn't matter. Let's just do it using the power rule and the chain rule. So this becomes minus half r squared plus a squared. Or you want to do the shortcut? Do you understand? Let me make sure you know what I'm saying. You understand that d over dx of square root x, or 1 over the square root x, is just 1 over x to the 3 halves multiplied by minus half, or no? It's okay, let's do it steps. So so this becomes minus half, right, r squared plus a squared minus 2ar cosine theta. So the minus half, so this becomes minus 3 halves times the chain rule. What's the chain rule? The chain rule is 2r, a squared is 0 minus 2a cosine theta. 2r, yeah, okay. And then, so that's the first one, and then we have the second guy. Let me make this a little bit bigger, we won't have room here. So plus the second guy is so there's a minus there, so it becomes a plus because there's a minus half. So this becomes 1/2 r squared plus ra over r all squared. minus 2RA cosine theta, and this is all raised to the 3/2, and then times the chain rule. R squared is 0. We have here with respect to R, so this will be 2AR, or 2A squared, 2A squared R, right? 2A squared R, because it's R squared over big R squared, minus the second term will be 2A cosine theta. Okay, so this is the derivative, yeah? Okay, let's evaluate this at R equals R. There's no need to simplify, so we get minus Q over 4 pi already, minus Q over 4 pi, and then if we plug in R for R, we get what's here, R squared minus half first, R squared plus A squared minus 2AR cosine theta to the minus 3 over 2 times 2R minus 2A cosine theta. Let me continue here, won't have room, plus 1/2 R squared. Now if R is R, these two go away and you get A squared plus A squared minus 2AR, well, this is minus 3 over 2 cosine theta to the minus 3 over 2, and if R is R, one of those go away and you get 2A squared over R minus 2A cosine theta, yeah? And I could factor out, you could see that those here are the same, so I could factor out this guy from both of them. So if I do that, we will get minus Q over 4 pi, and then we have a minus half out times R squared plus A squared minus 2AR cosine theta to the minus 3 over 2, and what we have left on the first guy is 2R minus 2A cosine theta. On the second one I need a negative sign because I factored out the minus, so minus 2A squared over R plus 2A cosine theta. And you could see that these two go away, and what do I have left? I have let's see, if I multiply, so common denominators here, and pull the R out, I will get my final answer will look like Q over you know, I could kill the 2 here, I could just cross out these 2's here, well, that 2 is already gone, I don't need it, so over 4 pi, and then this term comes down the same, so R squared plus A squared minus 2AR cosine theta to the minus 3 over 2, and if I multiply this guy here by R and this guy by R, I could pull out this R here, yeah, and I will have R squared minus A squared. This would be my surface charge density on the sphere. Questions on this one? Okay, so this is as a function. Oh, okay. So let's actually do something interesting. If we integrate this, okay, let's say we want to get the total induced charge. Okay, let's say we want to get the total induced charge. Now, what do you think the total induced charge will be? Q prime. It will be Q prime. That's, I mean, the whole method of images is making that assumption. We should get Q prime. Now, how do we figure out the induced surface charge density? Well, very simple. We integrate over the area. Yeah. So Q induced will equal Q induced should be equal integral of surface charge density dA. You agree? And we already have the surface charge density. So so let's see if we actually get what we expect we get. We know what we should get. This bad. Okay, we know that we should get Q prime. If these answers are correct, we should get Q prime. Yeah. Well, let's find out. So let's start the integration. So Q induced equals the integral. Okay. So let me pull out Q over 4 pi r. Now, by the way, r here is constant, yeah? A is constant, so I can pull all these out. And I have, because I'm on the surface of the sphere, so this integral is fairly straightforward. So I have r squared plus a squared minus 2ar, yeah, cosine theta to the minus 3 over 2. Now what's the surface element on the surface of the sphere? Well, let's say this is the sphere. If you're to just take a piece, yeah, r is not varying, right? So you have, so this here will be dr, and then this, if this is r, right, this is on the surface of the sphere, and this is d theta, this guy here will be r d theta. Oh wait, no, this is not r, this is r sine theta, right? So you'll get r sine theta d theta, because this is a spherical shape, right? You have to project the r first, the because technically it's basically this piece here, yeah. So this is theta, and this is here is r sine theta. Okay, so then dA will be r squared, which is constant, sine theta, right? And so I meant to say d phi, not dr. There's no dr because r is not varying. No? It's not varying. So r squared sine theta d theta d phi. What's varying here is theta and phi. Theta is going from 0 to pi, and d phi is going from 0 to 2 pi. Okay, let's see how we're going to integrate this. So this r squared, we can bring it out, so this guy goes away with this guy, and we have Q induced equals Q over 4 pi r times r squared minus a squared. Now this d phi term is easy, this will just get you 2 pi, yeah. and I already accounted for this r here. Yeah, and so what we have left is the integral of this d theta. Oh, and we have sine theta. Okay, nice. So u substitution should work out here, right? Fairly straightforwardly. So we have 0 to pi, because the derivative of cosine is minus sine. So r squared plus a squared minus 2ar cosine theta to the minus 3/2. Yeah? Times sine theta d theta. Okay, let's do it. Let's call this u. Yeah? So if u is r squared plus a squared minus 2ar cosine theta, that means du over d theta. I'll move the d theta on the right hand side, so this will be minus 2ar. Cosine is minus sine, so this becomes plus sine theta d theta. Divide by 2ar, so du over 2ar is equal to sine theta d theta. So we will replace this guy here with this guy here. Yeah, 2ar is a constant, we will take it out, and so the integral becomes, let me do the integral and I'll put it back there. So 0 to pi. Oh, let's change the bounds too. Yeah, we might as well, so we don't have to come back to these bounds. Okay, so if theta is 0, plug it in. What's u? If you plug it in here, u will be let's see. Yeah, this thing stopped working again. Second here. Okay, so we said we were going to change the bounds. Yeah. Let's do that. Let's change the bounds. If u is 0, if theta is 0, I meant, then u will be cosine 0 is 1, will be r squared plus a squared minus 2ar. And if theta is pi, then u will be cosine pi is minus 1, so this will be r squared plus a squared plus 2ar. Fair enough? Okay, great. So then our integral becomes from 0, or from 0 to pi r squared plus a squared minus 2ar cosine theta sine theta d theta. After the substitution, this becomes r squared plus a squared minus 2ar going to r squared plus, you don't have to change the bounds if you don't want to get that much clutter on the bounds. You can always go back to theta, but we've done it now, it doesn't matter. And we will get, so we'll save some clutter here on the inside, minus 3/2 u, and then du, and this is sine theta du, and then I can take out the 2ar. Yeah, so this here is 1 over 2ar u minus 3/2. Okay, and this integral, I hope, is very straightforward. Add 1, so you will get 1, so this becomes minus half. Divide by minus half or multiply by minus 2, and we will evaluate from r squared plus a squared minus 2ar to r squared plus a squared plus 2ar. Okay, and this 2 can cross out that 2, and we will get minus 1 over AR. U to the minus half. So what's U? U is R squared. It's up here. Yeah. U is R squared plus A squared minus. Oh, wait. No, let's evaluate with the U. We've already done it with the U. So let's evaluate with the U. So this is R squared plus A squared, upper bound first, 2AR, to the minus 1/2. Yeah. To the minus 1/2. So oh, and by the way, I'm on the sphere, so every R I could replace it with big R, yeah? Here. Right? Every R can go to big R now. Okay, so the minus half minus R squared. This big R too. Okay, R squared plus A squared minus 2AR, big R, to the minus half. Okay, and continuing on here, what do we get? Well, we could factor this out, yeah? So we have 1 over R plus A to the half. Agree? Minus 1 over, this also can be factored, R minus A, yeah, exactly, R minus A or A minus R to the half. Oh, I forgot the square. Wait, square half. Yeah, and this one is, oh yeah, so this one doesn't matter because it's a plus, but will this be R minus A or A minus R? Well, R is greater. And so this will be wait, no, I meant to say A is greater, because looking back at the figure, where's the figure here? We lost it. Let me confirm. Yeah, A is much greater than R, right? Because this is A here. Okay, so then in that case, I do have to switch these, right? This is A minus R squared to the half, after I take the square root, of course. Right, since A is greater than R. Okay, and then here we have minus 1 over, okay, almost there. So so this is Q induced, right? Or no, not Q induced. Oh, I haven't done the outsides yet. Okay, so common denominator, so these two will go away, so we will get minus 1 over AR, and common denominator will be A minus R plus A over R plus A, or A plus R. Let's switch these so it makes more sense. A plus R, A minus R. Yeah. The A's will go away. Wait, what goes away here? A minus R plus A. Oh, none goes away. None go away, yeah? We get minus 1 over AR. Factor out a 2, because it's 2A minus 2R over A plus R a minus r. Okay, and so this becomes minus 1ar. It's all algebra. Factor out the 2, so we have a 2 here. A minus r over a plus r. A minus r. These two go away, and we get minus 2 over ar a plus r. Okay, let's put this back in where did we stop? Here in this guy here. Okay, so we have 2 pi, we have a 2 left here, so q induced, let's copy and paste this down there, so oops, so we could see it. Yeah, copy, where am I here? Okay, let's see, paste here. Okay, so plug this here. So this was the value of this integral, so then I will have q induced is equal to, I don't need this arrow here, neither those zeros. So the entire answer for this integral is q over 2 r times r squared minus a squared, and the result for this was what? Minus 2 over ar yeah, ar ar times a plus r. Okay, and if we do that, we could factor, so this r can go with this r, the 2 can go out with the 2, and then I have minus left, q, and then r squared minus a squared is just r minus a, r plus a over a plus r. These two can go away, and we have left I'm getting an additional term here that I'm not supposed to get. Wait, where did it go wrong? This here is oh yeah, here I messed up with the signs, right? This is minus r minus a, and so the a's go away, and you don't have this. Okay, that explains it. So if you don't have this, then the r's go away, and we have minus 2 over a. There's no more r, this goes away, and this doesn't go away, correct? So this would be our final result here. Okay, let's see if this fixes it. So so this would be our final result. Plug it in here. So let's see, Yeah, yeah, it should fix it. So this becomes minus, we know that what the answer should be. So minus 2 over a, uh, let's take that out, and then here we have a plus r, a minus r. Yeah, and so this is yeah, so the 2's go away, qa, and this is a plus r, a minus r. So these can go away with a cost of a minus sign, and there's an r here that didn't vanish. Okay, good. So this minus sign is when we switch the r minus a into a minus r. Okay, great. So therefore q induced will equal minus q r over a. And what is qr over a, if you remember? Qr over a is q prime. So this is indeed equals to q prime. So this justifies the method. It's telling you that it's exactly what the method of images is trying to solve, that whatever you induce on the surface of a sphere is actually the charge that we had in the first place, and we are solving the potential force. So the initial assumption is correct. That's what we induce, and this induced charge, taken in the place of a sphere to solve this problem with just 2 point charges for simplification, actually redeems the process and works just fine. Yeah. Okay, great. Any questions on this?